Hi there, this is GCSE Physics. This is Atomic Structure Lesson 10. The title is Nuclear Fission and Nuclear Reactors. Objectives: to explain what nuclear fission is, to give examples of how we utilise nuclear fission, and to explain what a chain reaction is. Remember to pause at any point if you wish to make any notes. So let's start with nuclear power and power stations. So we burn fuel, so this is a general power station, oil, coal or gas, natural gas. So we burn the fuel to release thermal energy. The heat energy that's produced will turn water into steam, and then that steam turns a turbine. And electrical energy is generated. The turbine is connected to a generator. A generator is just basically a coil of wire with a magnet that spins around inside. You do that when you do if you do physics, you do GCSE physics rather than trilogy. You do that in electromagnetism. But basically, that's what we want that's what we want to happen. So what a power station should do is use the fuel, turn water into steam, turn a turbine. And nuclear power does that very effectively. Although we don't burn the fuel, it undertakes a process called nuclear fission. So this rather unremarkable rock on the right hand side is called uranium, and uranium is radioactive. You may notice, however, that it doesn't glow green. That's actually a myth, mainly perpetuated by The Simpsons. So nuclear fission is where a large, unstable nucleus decays into a smaller nuclei plus some thermal energy. The thermal energy released is used to heat water. This water turns to steam and turns a turbine. The turbine is connected to a generator and produces electricity. The really important part of that is the red bit on nuclear fission. So on the top right, you've got some raw, untreated or unprepared uranium. The bottom right is treated uranium that's going to be used for power production. If you like my Kim Jong-un gif, it's pretty cool. So nuclear fission occurs when a stable isotope is struck by a neutron. The isotope absorbs the neutron, becomes unstable, splits apart, and in that process it will release large amounts of energy. Unlike natural radioactive decay, fission is not a natural event. Two isotopes that undergo fission, and you need to remember these, include uranium-235 and plutonium-239. And the fission of 1 kilogram of uranium-235 releases more energy than burning 2 million kilograms of coal. It's quite stunning. So 1 kilogram of uranium, equivalent to burning 2 million kilograms of coal. And remember that an advantage of uranium in a nuclear power station is that it doesn't produce any carbon dioxide. It's not renewable. Obviously, the uranium, once it's used, can't be used again. But it won't contribute towards heating effect of the Earth. So what I want to do is to have a look at this decay equation. So this is an example of nuclear fission. Don't know if you've seen this guy on YouTube. Right, let's talk about the decay equation. So basically you've got a neutron adding to uranium-235. And what that will do is produce uranium-236. So as you can see, the mass numbers at the top have added together, and the proton number is still 92. So uranium-235 absorbs a neutron, becomes uranium-236. The uranium-236 is very unstable, and it will undergo nuclear fission. Splits into two daughter nuclei, the Ba and the Kr, which is barium and krypton. You don't need to know that. In an exam, it might give you the symbols, or it might be denoted with an X. So the daughter nuclei are barium-141 and krypton-92. We also get 3 neutrons being emitted, plus some energy. So if you see something like that in your examination, it might ask you to explain what's happening. So that's all I've done with the written content on the right hand side, is just explain what's happening. So neutron into uranium-235 produces uranium-236. You get barium and krypton 141 and 92 as daughter nuclei, plus 3 neutrons plus some energy. And the numbers, the 141 and the 92 and 3 lots of 1, will add together to give the 236 on the left hand side, and also to check the 56 and the 36 on the right hand side will add together to give 92 protons. Okay, so make sure you've got all that down and that's understood. Let's move on. So different uses. Fission typically has two uses. So you get controlled reactions, which is nuclear power stations, and uncontrolled reactions, which is nuclear weapons. So what's a chain reaction? So as you can see in the GIF on the right hand side, you've got a neutron being absorbed into a uranium-235 nucleus, becoming a uranium-236 nucleus, producing two daughter nuclides of barium and krypton, and three neutrons. And those neutrons are then being absorbed by more uranium-235, and what we've got is a chain reaction. And in reality, not all of the neutrons that are released will interact with an individual uranium-235 nucleus, but there is a critical mass, where the proportion of neutrons will interact with uranium to sustain a chain reaction. So a chain reaction is self-sustaining. Subsequent neutrons are released, and the fission process is repeated over and over. Controlled reactions occur in power stations. Uncontrolled reactions are used in nuclear weapons. And what you need to understand is that nuclear power stations can't actually explode like a nuclear weapon, because in a civilian power station, the amount of uranium-235, for example, is approximately 3% of the power supply, the fuel supply, sorry. The rest of the fuel is actually uranium-238, and when uranium-238 absorbs a neutron, it's actually stable. So we keep the proportion of uranium-235 relatively low so we don't have an accident. Nuclear weapons, on the other hand, have approximately 90% of uranium-235, which obviously is designed in that manner to give an uncontrolled reaction. You don't need to know the proportions, but I just thought a bit of background information about why that that process might be helpful. Okay, let's move on. So I just want to give some basics about how a nuclear fission reactor works. So for nuclear fission to start in a reactor, a uranium-235 atom must absorb a low-speed neutron. High-speed neutrons are not as readily absorbed by uranium nuclei. Basically, they scatter off the uranium-235 atoms, basically deflect off, and they're not absorbed. So we need to slow them down a little bit. So during a fission reaction, high-speed neutrons are released. So the reactor is actually submerged in water. The water is, the entire vessel thing. This is all water, submerged in water. And the water has two purposes. One, to cool the reactor down slightly. And secondly, it's called a moderator. And its job is to actually slow the neutrons down. So when it slows the neutrons down enough and they get down to a low enough speed, they'll be readily accepted by the uranium-238 atoms that are contained within the fuel rods, which in this image are depicted by the yellow bars. Now the control rods, the black ones, control rods are made of boron. And what boron does, it absorbs excess neutrons to prevent chain reactions getting out of control. If a chain reaction gets out of control in a civilian power station, it'll just get really hot. And when it gets really hot, the pressure will increase drastically, and then the vessel can just explode. So the concrete on the outside, if that explodes and the vessel explodes, you just end up with nuclear fuel all over the place, which is what happened at Chernobyl and Fukushima, the one in Japan in about 2011. So the control rods, you can get asked the question like, what if they are lifted out of the reactor or submerged into the reactor? If they're lifted out, there's obviously less boron, so the nuclear reaction will increase and we'll end up with more heat. And if you need to slow the reaction down, you can lower the control rods into the nuclear reactor to absorb more neutrons and to reduce the heat that's being produced. Anyway, I hope you found that helpful. So that's fission and fission in nuclear power stations. Thanks for watching, and I'll speak to you soon.